All right, in today's lecture, we're going to be looking at problems involving combinations and permutations. And we're only going to work out 2 problems because we've done more in the parent class. And this is just to kind of supplement that, to give you some more examples to work from. We've talked about the formulas for combinations and permutations in the parent class as well, and I'll remind you of them here. But the key thing that I want you to get away, to take away from this lecture is how to know when you should use a combination and how to know when to use a permutation. So remember, what we're doing in both of these cases is we're starting with a total number of objects, let's say, and we're choosing some subset of those objects. And we're basically asking how many different ways can I select R objects from a total of N objects. And the reason why we need to look at this in 2 different ways is because sometimes the order in which we select those R objects matters and we want to count accordingly. In other cases, the order of selection is not important and we don't want to count different orders of selecting the same subset as different possibilities. So let's start with this first case and we'll decide whether we need a combination or a permutation. It says, in how many ways can a team of 5 players be chosen from 8 candidates? So the total here is 8, and the subset that we're selecting is these 5 players. So we're choosing 5 players from a group of 8. Now, let's just say the players are denoted by letters of the alphabet. Player A, B, C, D, E, F, G, H. That's 8 letters, right? If I select players A, B, C, D, and E, that's going to form the exact same team as if I selected them in reverse order, E, D, C, B, A. I don't want to count those 2 arrangements as different because the end result is still the same team. The order that I selected the team members doesn't change the outcome. So what that means is I want to select whichever of these 2 formulas does not care about the order of selection, and that would be combinations. So what is the formula for a combination? Here's the general formula. NCR, we read this as N choose R, and it's equal to N factorial, N being the number representing the total that we're choosing from, over R factorial, where R is the number from that total that we're choosing, times N minus R factorial. In our case, we're looking at 8 choose 5. 8 players, and we're choosing 5 from those 8 to form a team. That's equal to 8 factorial over R, which in this case is 5 factorial, times 8 minus 5. That's N minus R factorial. Okay, deal with the parentheses first. I have 8 factorial over 5 factorial times 3 factorial. Okay, now last week we looked at how to evaluate factorials involving quotients like this by hand very easily. Remember what we did is we wrote out the numerator, which in this case would look like 8 times 7 times 6 times 5 times 4 times 3 times 2, all the way down to 1. And then I do the same thing for my denominator, and I look for things that cancel. I'm going to look at the larger of these 2 factorials down here and cancel that with part of what's in my numerator. Notice that if I cancel 5 times 4 times 3 times 2 times 1 from my numerator, I'm going to be left with just the 8 times 7 times 6. Everything that would have come after that in my factorial is going to cancel with that guy right there. Now what's left? Well, down in my denominator, I have 3 times 2 times 1, because that's what 3 factorial is, and I haven't touched the 3 factorial yet. However, again, ignore the 1, because in multiplication it won't change anything. 3 times 2 is equal to 6. So this entire denominator is equal to 6, which can cancel with that 1 6 right there, leaving me with 8 times 7, which is equal to 56 different teams. I'll just say it's 56 teams. Okay, so if I have 8 players to choose from, and I want to choose 5 of those 8 to make a team, I have 56 different possible teams that I could choose. Okay, this was fairly straightforward and rather simple. There's not a ton of steps here. And the exact same problem could have been solved using systematic listing. I could have listed out all 56 possible teams. But that's 56 things that I have to list. And that's a lot of work for something that does not need to take that much work. That's what the power of these combination and permutation formulas are. Let's take a look at another problem. This one's a little bit more complicated because we do need to decide between a combination or a permutation, but that's not the only part of our answer. We're going to decide whether we need a combination or a permutation, and then there's more that has to happen in addition to that to get an answer. And this is where the more interesting counting problems come from, problems like these. So it says Avery and Beth are joining 5 friends at a concert. If Avery and Beth wish to sit next to each other, how many seating arrangements are possible for the group in a row of 7 seats? So there's a total of 7 friends here. 2 of them we know their names, and then the other 5 are nameless for us. But that's a total of 7 people. And we know that they want to occupy a row of 7 side-by-side seats. We're kind of told that in the problem. But in addition to that, there's this extra condition that's imposed on this. The nameless 5 friends can sit anywhere in that row, but we want Avery and Beth to be sitting next to each other. So somehow that's going to affect our total, because if you just look at the total number of ways of arranging 7 people in a row of 7 seats, a lot of those arrangements will have Avery and Beth separated. So if we just did 7 factorial, which is the number of arrangements of 7 friends in their seats, that's going to overcount, where we have possibilities in there that we want to disregard. So let's think of this in a different way. Using a technique we've already seen before, I'm going to make 7 underscores. 1, 2, 3, 4, 5, 6, 7. And I'm going to think of these as the 7 seats in that row. Okay? Now, I want to look at the total number of ways that Avery and Beth can be sitting next to each other first. And I'm going to ignore the other 5 friends just for a moment. If you look at it, there are 6 pairs of side-by-side seats. 1 here, 1 there, 1 here, 1 here, there, and there. 1, 2, 3, 4, 5, 6. 6 pairs of side-by-side seats. So what that means is there's a total of 6 seats, or 6 positions that Avery and Beth can be. Let me say that differently. There's a total of 6 pairs of seats that Avery and Beth can choose to sit in, so that they're side by side. Okay, 6 total. However, once they choose whichever pair of seats they want to sit in, they then have to decide who is going to sit on the left and who is going to sit on the right. So for those 2 friends, there is a total of 2 factorial different arrangements of those friends in the pair of seats that they choose from. And I'm using multiplication here because that's what our fundamental counting principle would tell us to do. They first choose a pair of seats, and then once they have done that, they choose how they arrange themselves in that pair of seats. So that's 2 independent events. We multiply those. Once Avery and Beth have chosen whichever seats they want to sit in, let's just say it's these 2 for one of the possibilities. That leaves 5 remaining seats in which the friends want to, or which their 5 friends need to rearrange themselves. Now, in this case, we could frame this in terms of a permutation, but we don't really need to because it's an arrangement of 5 seats, and we know that there's 5 friends. So if you were going to think of it as a permutation, it's like it would be this. I'm going to write it down here. 5p5. We have a total of 5 friends, and we want to look for 5 total arrangements of those friends. And just as a reminder of the formula for a permutation, it's equal to n factorial over n minus r factorial. In our case, that would look like 5 factorial over 5 minus 5 factorial. Or in other words, 5 factorial over 0 factorial. Now, I believe we discussed this in the parent class, but even though your gut is your gut wants to tell you that 0 factorial is equal to 0. It is actually not. It's equal to 1. And that is a matter of definition. It's not something that we prove. We define it to be equal to 1. This becomes 5 factorial over 0, which is just 5 factorial. But that should not be surprising because, again, we have 5 seats and 5 friends. So we're looking at the total number of ways to arrange 5 friends in a row, which we already knew was 5 factorial before we even talked about permutations. So this becomes times 5 factorial. Okay, now what is this? 2 factorial is just 2 times 1, which is obviously 2, and 6 times 2 is 12. So that's equal to 12. In last week's lecture, the very first problem we did was 5 factorial. That came out to 120. If I ignore the 0 on this, that's 12 times 12, which from my multiplication tables, I know by heart that's 144. And then I put a 0 at the end of that to get 1440. So that means there's 1440 seating arrangements. Okay? So again, in this case, we could have thought of one of the parts of this problem using a permutation because it involved an arrangement of people in seats. Because different arrangements are counted separately, that's a case where order matters, and that's where the permutation formula comes into play. But because we had the same number of people as we did seats that we were trying to arrange them in, that permutation reduced down to just a single factorial anyway. So we could have just thought of it like this. But that's going to wrap things up for this week.